what happens when we press a key on the keyboard? How does that turn into a character we can see on the screen? In the 80s, when hardware was limited, the software had to do some clever tricks to read the keyboard. Electrical signals would strobe through columns of keyboard switches one at a time. Code would have to compensate for slow human speeds and unstable electrical connections. Key combinations and caps lock had to be interpreted. And the TRS-80 color computer had its own issues, with joystick buttons being wired up into the same circuits as portions of the keyboard. Then the Dragon computer came along and added its own refinements and the new feature of auto-repeat, implemented with a rather creative approach. Today we illustrate all these smart ideas with visuals so simple anyone can understand. And we'll explore exactly how the Dragon computer improved on its CoCo predecessor. The basic interpreter on the CoCo uses a routine in the ROM to read what the user is typing at the keyboard and to convert it into an ASCII character code. It's called POLCAT. Pol for character at terminal, I guess. We'll be exploring the steps POLCAT takes to convert electrical signals sent through the keyboard traces into ASCII character codes useful to basic programs and the rest of the ROM for printing and evaluating. The keyboard is a series of switches arranged in a matrix. A strobe consists of sending out a low signal through the columns of this matrix, usually just one column at a time. When a key is down, it closes a circuit that connects the trace from the key's column to its row. The software reads the signal at the rows to detect if this happened. This is all done with hardware registers, which look to the software like memory locations it can read and write to. The software performs a strobe by writing a byte to a hardware register, and then reading another hardware register containing the response. And that's exactly what POLCAT does. It strobes each column, writing a single 0 bit for the column it's strobing, and looking for a 0 bit in the row response. Once a column strobe results in a 0 bit for one of the rows, a key press has been detected, and we're done strobing. If you'd like to go deeper down into the assembly code, I have a video specifically about keyboard strobing, and there's a link in the description. POLCAT maintains a key buffer in memory, where it remembers the results from the last time it did keyboard strobes. 8 bytes for 8 column strobes. Each time a strobe finds a key down, POLCAT performs a dedupe. It compares the result of that column strobe with the key buffer's copy of the last time that column was strobed. Only if there's a new 0, which means a new key is down in that column, will POLCAT accept that a key is actually being pressed by the user. The idea is that POLCAT is called so frequently that no human typing will be fast enough to lift the key before POLCAT is called again to see that the key is still held down. And even the next time it's called and the next time it's called, the key will still be held down because the user is just not fast enough. So this deduping step is about finding differences. It's looking for the first column strobe that results in a 0 bit, meaning a key that's down now, that wasn't a 0 bit last time. Once it finds such a key, then it goes on to the next step. A good way to understand deduping is to see what happens when we don't do it. This is my actual CoCo running an app that uses a copy of POLCAT but with all the deduping stuff removed. So if I try to type the alphabet, you'll see I cannot control this at all. And if I very gingerly just try to bounce as quickly as I can, there's just no way I can get a single letter, although maybe I can come close. No one could ever possibly use this for anything. Ultimately, POLCAT must output the ASCII code that corresponds to the key press it detects. To help with this, Polecat numbers the matrix positions from 0 to 50. These are not the ASCII codes for the keys, but they help. This contiguous block of keys corresponds to this contiguous block of ASCII codes. Same for this block. Polecat uses these blocks to efficiently find the right ASCII code with simple arithmetic. Polecat also does a special strobe just for the shift key. It takes the result of that strobe and the current state of the caps lock flag in memory to decide if it needs to adjust the ASCII code that it calculates. Some keys don't fall within a convenient range and have to be special cased in this table. Interestingly, 0 is special cased as well, since Shift 0 is the caps lock on the CoCo. Keyboard keys are nothing but switches. That means they are susceptible to contact bounce or chatter. As the metal closes or opens the switch, there is a mild bounce that can cause momentary fluctuations of the current before it settles on its new state. The keyboard is pulled so quickly and so frequently that these fluctuations can be picked up and misinterpreted as the key rapidly going up and down. This is easily fixed in software by double-checking that a newly detected key press is real. We just wait a short delay and then do another hardware strobe to see if this new key we detected is actually a stable state. That's called debouncing. The CoCo's implementation of this, though, is rather curious because it combines debouncing with a joystick button check. Let's talk about joystick buttons. The CoCo supports 2 joysticks, each with a single button. Each joystick button is wired directly to the same hardware register that we read when detecting keyboard key presses. Push a joystick button, and a 0 comes out on its corresponding row, even though we didn't strobe any columns with a 0. So we can detect a joystick button press by not sending a signal through any of the columns, but then noticing that a signal still came out through one of the 2 bottom rows. The original keyboard driver in the first version of the ROM completely ignored this fact, and if you were to push a joystick button at the basic command prompt, you would see a rush of characters. These are the very characters that live on the row the joystick button is wired up to. This was fixed in later versions of the ROM as follows. During the debounce check, Polecat looks for a low signal coming out of one of the bottom 2 rows without first strobing any columns. If such a signal is found, a joystick button must be down, which corrupts our ability to detect any actual key presses. So the whole keyboard pull is abandoned. With that, now let's look at everything that happens during the debounce step. Remember, at this point, Polecat just calculated the ASCII code for the key it thinks has been pressed. Now, in order to do the debounce, it counts down from 1118 to create a short pause. But then, instead of restrobing for that key immediately after, it does a joystick button check first. Without sending a signal down a column, check if a signal still comes out either joystick row. If either joystick button is pressed, Polecat forgets about the key press it just translated into ASCII and returns nothing. If a joystick button is not pressed, then Polecat restrobes the column it found a key press in. This is the debounce. If the restrobe gives a different result, then, again, Polecat forgets about the key press and returns nothing. But if the strobe result is the same, the key press is now vetted and passes the debounce check. Couple things. First, why are we waiting until now to do the debounce? Why go through all the trouble of converting to ASCII if we might need to throw all that work away if we detect chatter? Second, why are we waiting until now to do the joystick button check? The steps are, first, we're detecting a key press, pausing, checking for the joystick button, and then rechecking the key press to do the debounce. Why is the joystick button check mixed up in the middle of all this? I don't know. But remember, the joystick button check was added to a later version of the ROM, after the first version had already been released. Maybe there were limitations where they could add new code. Maybe if they had a separate joystick button check apart from the debounce, it would have moved things around and entry points would have changed and they just couldn't tolerate that. In any case, the Dragon definitely had its own ideas about the right way to do all of this. More on that later. But for now, let's see what happens if we turn off debouncing. Once again, this app is using a copy of Polecat, but there's no debounce happening. Other than my typing mistake, it seems like everything is kind of just fine. If I try to very slowly push it down and lift it up slowly, I can't seem to get doubling happening here. I don't know if the deal is that my hardware is just in really good shape, or maybe we just did not need to do debouncing at all. If any of you know why debouncing wouldn't actually really even have an effect on the CoCo, I would love to find out. Feel free to let me know what you know. Finally, Polecat analyzes the results of the column strobe and the shift strobe it's already done. If it detects that Shift 0 has been pressed, that's interpreted as a caps lock on the CoCo. So at this point, Polecat updates the caps lock flag in memory, which will be used when interpreting future key presses. The Dragon computers, manufactured in Wales by Dragon Data, were Europe's answer to the CoCo. Not quite clones of the CoCo, they still retained nearly all of the original design, including the same CPU, video display generator, and importantly, the Motorola 6883, which orchestrated memory use between the CPU and other hardware. One of the very few hardware differences is how the keyboard is wired up. The Dragon's matrix is similar to the CoCo's, except, let's see, these rows need to move down, and we'll shift those into place. There we go, the Dragon matrix. In terms of software, Dragon licensed the same Microsoft Color and Extended Color basic ROMs as the CoCo. While Dragon made modifications to these, many routines remained the same. For example, they use identical code for their flood fill algorithm, which you can explore in this video. See the link in the description. But the disk commands and floppy controller are completely different, and so is Polecat. Certainly Polecat had to change to work with the new keyboard matrix, but the differences go far beyond that. These are the steps we went over for the CoCo. Let's see how they map onto the Dragon. The Dragon does the joystick button check early on, allowing it to skip everything else if it detects the joystick button is down. This makes more sense than checking it later like the CoCo does. Then, the Dragon does the same kind of hardware strobes and deduping as the CoCo. But then, before doing any ASCII conversion, the Dragon does the debouncing. Again, smarter than the CoCo, because if we detect chatter, the ASCII conversion would have been wasted work. Only now do we do the ASCII conversion, which is similar to the CoCo, but adjusted to work with the different matrix, and then update the caps lock flag in memory. But there's more! Before the Dragon does any of these steps, it does the any key check. Dragon's Polecat starts by sending a 0 on every single column simultaneously to see if any of those signals reach the rows. This is a nifty optimization because this can be done with a single write and read, and nearly every time Polecat is called, no key will be down anyway. Human speed pales in comparison with even 80s computer speeds, so if Polecat is called 50 or 100 times a second, nearly all of those times the human will be between keystrokes. This allows us to avoid wasting time doing 8 separate column strobes, requiring 8 separate writes and reads, for the typical case when there's nothing to find. Of course, the any key check can't tell us exactly which key is down, because we won't be able to distinguish between 2 keys in different columns, but which happen to line up in the same row. They're going to trigger the same row bit. So we will still need to do the separate column strobes later to isolate exactly which key is down, but only if we detected activity during the any key check. But this any key check isn't just looking for keys down, it's looking to see if a new key is down. Remember the key buffer used to dedupe or test whether a key is down now that wasn't down the last time Polecat was called? The Dragon does the same thing, but instead of reserving just 8 bytes for the 8 column strobes it's about to do, it also reserves a 9th byte up top for the any key check. The any key check looks to see if the result differs from the any key check last time Polecat was called. If so, that counts as activity, and we move on to the next step, and eventually do the individual column strobes. Otherwise, Polecat immediately returns with no result. Although this any key check is a nice optimization, it can lead to inconsistent behavior. So I'm going to press W and hold it down while I repeatedly press V, which happens to be in the same row. You'll see that the any key check does not detect that there was a change, so the V doesn't register. However, if I press W and hold it down, while repeatedly pressing the O key, which is in a different row, that does get detected by the any key check, so Polecat continues to the separate column strobes to distinguish what the change was, and the O key gets returned. And there's one last step added to the Dragon 64. Initialize the auto-repeat countdown. Unlike the CoCo, the Dragon 64 supports auto-repeat. I don't have a Dragon 64, but I do have XRoar, which is the next best thing, and here I've booted up the Dragon 64 machine. Now if I press a key and hold it down, it's not going to auto-repeat. But if instead I first run exec, there is a routine that exec is primed to execute on startup that changes the Dragon 64 into 64K mode. You'll notice now my cursor is blinking blue, and now if I hold down a key, it repeats. Auto-repeat works by tampering with the key buffer that is normally used to dedupe. This makes sense because auto-repeat and dedupe are mortal enemies. Dedupe forces Polecat to process only changes to the keyboard state, while auto-repeat wants Polecat to process an unchanging keyboard state as the same key remains held down. Now we can't just eliminate the key buffer. Recall what happened when we tried that earlier. Polecat gets called so frequently no human could react fast enough to control how many times a key is repeated and to avoid a repeat in the first place. So the Dragon employs a clever algorithm to carefully clear out the key buffer at exactly the right time. This auto-repeat init step at the end of Polecat examines the outcome of all the previous steps. If no new key was detected, then there's nothing to do and Polecat is done. Otherwise, if Polecat detected a key press and is about to return its ASCII code, Polecat first initializes a special delay countdown. The Dragon has a built-in timer which goes off 50 times a second. Lots of useful work happens each time it fires, for example to aid with video display and music, so auto-repeat takes advantage of this timer too. Whenever the timer goes off, if the auto-repeat delay countdown is in effect, the timer decrements the countdown by 1. And once the countdown hits 0, that's when the timer wipes the key buffer. The effect of this is that the next time Polecat is called, if the user is still holding down the key, it will be interpreted as a new key down, and it will be processed as if the user had lifted up and pressed that key again. There are some extra smarts to remember which key is being auto-repeated, so the countdown can purposely be made much higher if this really is a new held key versus a key that's already been held down for a while. That way the user has to hold the key for a countdown of 40, which would take nearly a second, before the auto-repeat kicks in. And once it does kick in, the key now repeats after each countdown of 5, about 1/10 of a second. Fast, but not so fast that the user has no control over stopping it at the right time. And that's auto-repeat. There are other smaller changes with the Dragon's Polecat, like how the Debounce pause is significantly shorter on the Dragon than on the CoCo, and how the ASCII conversion had to be rewritten to account for the rearrangement of the rows in the matrix. But otherwise, that's it. You can learn more about CoCo's Polecat and all its other ROM routines from the Unraveled series. And the original source for Dragon's Polecat and its other ROM routines are up on GitHub. Find links to those and other resources in the description. I hope you found this interesting, and as always, thank you for watching.